Our modern world rests on foundations laid thousands of years ago. The concrete beneath our feet, the clock on your wall, even the zero in your computer code, all trace their origins to ancient minds. This journey uncovers 25 forgotten technologies that are not museum pieces, but blueprints for modern innovation. You will discover how a 2,000-year-old self-healing concrete is revolutionizing material science, and how a mysterious bronze device found in a shipwreck functioned as the world's first computer. We are standing on the shoulders of engineering giants whose brilliant solutions to timeless problems are more relevant than ever. What ancient invention do you believe has most shaped our daily life? That profound understanding of the natural world was their greatest laboratory. Ancient engineers did not have digital simulations or synthetic composites. Instead, they possessed an intimate, hands-on knowledge of the materials and forces around them. They watched how water flowed, how plants grew strong against the wind, and how the sun cast shadows across the seasons. This deep observation was coupled with relentless experimentation. A project might not succeed many times, with each challenge teaching a crucial lesson about stress, balance, or material properties. Their brilliance lay in interpreting these natural clues and persisting until a solution emerged, one that was often both elegantly simple and astonishingly effective. Think of a Gothic cathedral soaring towards the heavens. Its incredible height was not a reckless gamble, but a calculated mastery of physics. The flying buttress, an external stone support, acts like a pair of steadying hands on a tall, heavy bookshelf, channeling the immense weight of the walls safely down into the ground. This was not magic, it was applied geometry and a profound understanding of load and counterforce, all achieved centuries before the formal laws of physics were written. Similarly, the sprawling networks of canals and aqueducts from Mesopotamia to Rome were feats of precise gravitational engineering. Builders had to calculate minute slopes over vast distances, ensuring a steady, reliable flow of water for entire cities, using little more than sighting tools and generations of accumulated knowledge. This foundational ingenuity, born from necessity and a deep connection to the environment, is the very bedrock of our modern world. It proves that the spark of innovation is a continuous thread woven through human history, a legacy of problem-solving that connects us directly to those master observers of the past. And one of the most enduring examples of their material genius lies beneath our feet, a 2,000-year-old secret that we are only now beginning to fully replicate. The Pantheon's dome in Rome has withstood the elements for nearly 2,000 years. A silent testament to an engineering secret modern science is only now unraveling. While our own concrete structures crumble and crack within decades, this ancient marvel stands strong thanks to a revolutionary self-healing formula. Roman concrete was a masterful blend of volcanic ash, lime, and seawater. This specific mixture triggers a chemical reaction over time, creating a rare mineral called aluminous tobamorite. The true genius, however, lies in its response to wear. When tiny fissures form, moisture seeps into these microcracks. Instead of causing further deterioration, this water activates a continuing chemical process. New crystalline structures grow, seamlessly filling the gaps and effectively mending the material. It is a living substance, in a sense, one that grows stronger with age. Today, material scientists are actively decoding this ancient recipe. Their goal is to replicate this self-healing property in modern infrastructure. Imagine bridges, roadways, and buildings that can repair their own wear and tear. This would not only create vastly more durable constructions, but also dramatically reduce the immense environmental cost of constant maintenance and rebuilding. The legacy of Roman concrete is a powerful reminder that sometimes the most advanced solutions are waiting for us in the past, offering a blueprint for a more resilient future. That same principle of harnessing natural power for lasting effect can be seen in another ancient innovation, one that captured the very wind itself. Recovered from the deep in 1901, a lump of corroded bronze from an ancient shipwreck held a secret that would take over a century to fully understand. This object, known as the Antikythera Mechanism, was at first thought to be a simple nautical timekeeper, but when researchers finally looked inside using advanced imaging technology, they uncovered a labyrinth of interlocking gears, a miniature mechanical universe of breathtaking complexity. It was not a clock, but a calculator, an intricate analog computer designed to model the heavens. With a turn of a hand crank, its dozens of bronze gears would spin in perfect synchrony, predicting the movements of planets, the phases of the moon, and even the timing of upcoming Olympic Games. This was not simple astrology, it was precision engineering of the highest order, a physical simulation of cosmic cycles built 2,000 years ago. The sophistication of this device would not be seen again until the mechanical clocks of medieval Europe, over a millennium later. Its very existence reshapes our understanding of ancient technological capability. Today, the principles embedded in those ancient gears are more relevant than ever. The concept of miniaturized, interlocking systems for precise calculation directly inspires modern robotics and precision engineering, where complex movements must be coordinated with flawless accuracy. The Antikythera Mechanism stands as a powerful reminder that the drive to model our world, to compute the seemingly incalculable, is a deeply human impulse that transcends the ages. From a device that calculated the cosmos using the power of gears, we find another ancient innovation that drew power directly from the Earth itself. Rising from the sun-baked rooftops of ancient Persian cities, slender towers stood as silent sentinels against the desert heat. These were the Badgers or Windcatchers, and they were masterpieces of passive climate control. Their design was deceptively simple, a tall structure with openings facing the prevailing winds, but the true genius was in how they harnessed the elements. As warm, dry air was captured at the top, it was funneled down a central shaft and into the heart of the building below. Often, this shaft would direct the airflow over a pool of water or a Qanat, an underground canal. Here, the magic of evaporative cooling took place. The air would shed its heat, becoming cool and moist before gently circulating through living spaces, dropping indoor temperatures by a remarkable margin without a single watt of electricity. This was not just air conditioning, it was architectural poetry, a seamless dialogue between a building and its environment. Today, this ancient logic is experiencing a powerful resurgence. In an era of rising energy costs and environmental concerns, sustainable architects are looking back to the Windcatchers' principles. Modern interpretations, sometimes called solar chimneys or passive downdraft cooling towers, are being integrated into green buildings worldwide. They work on the same fundamental physics, capturing cooler, denser air at night to ventilate a structure or using water evaporation to provide natural cooling. By reducing our reliance on power-hungry mechanical systems, these designs point toward a future where our buildings can breathe with the climate once more. This ancient mastery of a single, vital resource, air, was part of a much broader and more complex system of managing the most precious desert resource of all, water. While the Windcatchers cooled the air above, a hidden network of tunnels worked silently below to deliver life itself. These were the Qanats, one of the most enduring and sustainable water systems ever conceived. In the heart of arid Persia, ancient engineers did not fight the landscape, they collaborated with it. They began by locating a water source at the foot of a mountain. Then, with remarkable precision, they dug a gently sloping underground tunnel, just deep enough to tap into the aquifer. A series of vertical access shafts were created along the tunnel's path, serving dual purposes. They provided air for the workers and allowed for the careful removal of excavated soil, while also marking the tunnel's invisible course across the desert surface. The slope was the system's engine, a masterpiece of gravitational engineering. It was calculated so carefully that water would flow steadily for dozens, sometimes even hundreds of kilometers, all without a single pump. Because the water traveled entirely underground, it was protected from the relentless desert sun, eliminating the massive evaporation loss that affects open canals. For centuries, this silent, subterranean river sustained entire cities and turned barren lands into flourishing agricultural centers. Today, as many regions face severe water scarcity, engineers are looking back to the Qanat with renewed respect. This ancient approach offers a powerful model for modern water management. The idea of using gravity-fed systems to transport water without energy consumption while protecting it from evaporation is a profound lesson in resource conservation. It demonstrates that sustainability is not a new invention, but often a return to timeless principles of working in harmony with the natural world. After mastering the flow of water, another ancient civilization turned its attention to a different kind of current, one that carried not water, but the very words of an empire. High in the Andes, the Inca Empire managed a vast territory without a single sheet of paper or a written word. Their administrative genius relied on an elegant and mysterious technology, the quipu. A quipu was a collection of colored cords, often made from cotton or llama wool, from which hung a cascade of pendant strings. Each element of this device was a carrier of information. The colors of the cords, the types of knots, their specific placement along a string, and even the spin and ply of the fibers themselves held distinct meanings. This was not mere decoration, it was a sophisticated, three-dimensional language of data. Skilled interpreters, known as quipukamayaks, could run their fingers along these knotted strands and decipher intricate records. They could recount census data, track vast stores of grain in imperial warehouses, and document complex historical narratives and ceremonial calendars. It was a tactile, portable database for an entire civilization. Today, researchers view the quipu not as a primitive tool, but as a profound precursor to non-textual data storage. Its logic inspires modern computer scientists exploring new ways to represent information. The idea of using physical attributes like color, texture, and spatial relationships to encode data challenges our reliance on flat screens and binary code. It opens doors to tactile interfaces for the visually impaired and influences concepts in areas like biomimicry, where data might one day be stored in the very structure of a material. The quipu stands as a testament to human ingenuity, proving that language and memory can take forms far beyond the written word. This ancient method of storing complex information in a physical object leads us to consider another kind of storage, one that captured not data, but the very power of the sun. Within a clay jar unearthed near Baghdad lies a mystery that could rewrite the history of technology. This simple object, known today as the Baghdad Battery, consists of nothing more than an iron rod suspended inside a copper cylinder, sealed within a ceramic vase. If this vessel were filled with an acidic liquid like vinegar or wine, something remarkable happens. A subtle chemical reaction occurs, generating a small but measurable electric charge. While scholars still debate its original purpose, perhaps for electroplating metals or for ceremonial sensations, its significance is undeniable. This artifact proves that the fundamental principles of electrochemistry were understood and potentially applied nearly 2,000 years before Alessandro Volta invented the modern battery. The very existence of this device challenges our linear view of scientific progress. Today, this ancient spark of inspiration is guiding research into simple, sustainable power. Engineers are exploring low-cost, non-toxic batteries using organic materials for applications in remote areas, providing basic electricity for medical sensors or data loggers where complex infrastructure is impossible. It is a powerful reminder that innovation is not always about creating more power, but about harnessing the power that is already within our reach. This ancient understanding of controlled energy finds a parallel in the way entire cities were designed to harness a different kind of power, the organized flow of human life. Amidst the clash of ancient naval battles, one weapon inspired a unique kind of dread. Greek fire was the closely guarded secret of the Byzantine Empire, a liquid flame that could not be put out by water. Projected through bronze tubes mounted on their warships, this substance would cling to enemy ships and even burn as it floated on the sea itself, creating a formidable and unstoppable blaze. The exact recipe was a state secret of such immense importance that its composition was known only to a very few and was ultimately lost to time. Modern analysis suggests it was likely a petroleum-based naphtha, mixed with other substances like resin or quicklime that allowed it to ignite upon contact with water and adhere so tenaciously to its targets. While its primary use was undeniably military, the sophisticated chemistry behind this ancient innovation holds unexpected relevance today. Researchers studying its legendary properties are not seeking to recreate the weapon itself, but to understand the principles of its persistent, adhesive burn. This knowledge directly informs the development of modern fire-retardant materials, helping to create safer textiles and building supplies that can resist ignition. The same chemistry inspires work on powerful industrial adhesives that can bond in wet conditions, and it even finds a place in controlled burn techniques used in agriculture and land management, where containing a fire's spread is critical. The legacy of Greek fire is a complex one, a reminder that the same fundamental knowledge can be channeled toward very different ends, from conflict to protection. This mastery of controlled combustion required an equally sophisticated understanding of controlled creation, a precision that found its ultimate expression in the hands of another ancient culture. A brass disc etched with a delicate web of lines and curves could once hold the entire night sky in the palm of your hand. This was the astrolabe, the smartphone of the medieval world. More than just a navigational aid, it was a portable cosmos, a two-dimensional model of the universe built from mathematics and metal. A user would suspend the instrument and align its sighting bar with a known star. By rotating the device's intricate, layered plates called tympans, they could calculate the time, predict the sun's path, and even determine their latitude on the spinning Earth. Each plate was custom engraved for a specific latitude, a physical database of celestial coordinates. This was not a tool for mere observation, but for active calculation, an analog computer that translated the heavens into actionable data. The astrolabe's genius lies in its user interface, a beautiful synthesis of complex information into an intuitive, tactile experience. This elegant problem-solving, making the immensely complicated feel simple and accessible, is a core principle in modern software design. Engineers creating complex dashboards for pilots or data visualization tools for scientists strive for that same clarity, turning overwhelming streams of information into a clear, actionable picture. The astrolabe reminds us that the best technology does not just compute, it communicates, bridging the gap between human intuition and cosmic complexity. After such a device for charting the heavens, another ancient innovation offered a way to chart the very land beneath our feet. The same principles of durable, intelligent design that built the Pantheon were laid down across the landscape itself, in stone pathways that still shape our world today. Roman roads were far more than simple dirt tracks. They were the empire's circulatory system, engineered with a foresight that modern civil engineers still admire. Their construction was a meticulous, multi-layered process. Workers would first excavate a deep trench and pack it with a foundation of large stones. Upon this, they laid successive layers of smaller gravel, sand, and finally, a surface of tightly fitted, interlocking stone slabs. This entire structure was ingeniously cambered, meaning the center of the road was slightly higher than the edges. This subtle curvature acted as an instant drainage system, channeling rainwater away to prevent erosion and preserve the roadbed. The result was a resilient, all-weather highway built to last for centuries, and many of them have. This network of over 400,000 kilometers did more than just move legions swiftly. It facilitated the unprecedented flow of goods, ideas, and information, effectively creating the first integrated European economy. The very concept of a connected infrastructure grid, a web of reliable routes binding distant regions into a cohesive whole, is a direct legacy of the Roman system. Today, the principles of deep foundations, proper drainage, and layered construction remain the gold standard in road building, a testament to a solution so effective it has endured for 2 millennia. This ancient mastery of moving people and goods across continents finds a fascinating parallel in a much smaller, more personal innovation, one that revolutionized individual transit and reshaped societies across the globe. A simple metal loop hanging from a saddle revolutionized humanity's relationship with the horse, and in doing so, reshaped the world. The stirrup, an innovation that likely emerged from the steppes of Asia, provided a rider with something they had never truly possessed before, a stable platform. By offering both lateral and frontal support for the feet, it locked the rider securely onto their mount. This was not merely a matter of comfort, it was a fundamental shift in control. A warrior could now stand in the saddle, bracing themselves to wield a heavy lance or swing a sword with full force without the constant fear of being unseated by the impact. This simple interface gave birth to the era of shock cavalry, where armored knights could become a single, devastating projectile, changing the very dynamics of battle and the structure of medieval societies. But the legacy of the stirrup gallops far beyond the battlefield. Its core principle, enhancing human control and stability through an intuitive physical connection, is a cornerstone of modern ergonomics. Think of the pedals on a bicycle designed to cradle your foot and transfer power efficiently with every rotation. Consider the carefully positioned foot pegs on a motorcycle, giving the rider a firm base to lean into a curve. This same logic extends into the operating room, where surgeons rely on stabilized supports for their arms during delicate procedures, and into the cockpit of an aircraft, where pilots need a secure and responsive interface to command complex machinery. The stirrup taught us that a small, thoughtful support can amplify human capability to an extraordinary degree. This ancient quest for control over powerful forces finds a parallel in the next great challenge our ancestors faced: the monumental task of controlling water itself. A simple spiral enclosed within a cylinder solved one of humanity's oldest challenges. Archimedes' Screw, a device of elegant genius, uses a rotating helical surface inside a pipe to lift water effortlessly from a low body to a higher channel. As the screw turns, each successive pocket of water is trapped and gently carried upward until it pours out the top. This was not a machine that demanded immense power. It was a triumph of geometry and patience, capable of being turned by a single person or a beast of burden. For over 2 millennia, its fundamental design has remained virtually unchanged, tirelessly moving water for irrigation and supporting early communities across the ancient world. Its endurance is a testament to a perfect marriage of form and function. Today, you can still find this ancient technology hard at work in modern water treatment facilities, where its gentle, non-clogging action is ideal for moving thick mixtures and organic matter. It powers agricultural irrigation systems in regions where electricity is scarce, lifting water from canals to fields with a simple, reliable motion. But the influence of that brilliant helix extends far beyond moving water. The core principle of a rotating spiral to transport material is now embedded in industrial conveyor systems that move everything from grain and coal to powdered chemicals. More remarkably, this ancient geometry is being studied for advanced aerospace applications, where continuous spiral propulsors could offer new modes of efficient propulsion for aircraft and underwater vehicles. From the sun-baked fields of antiquity to the cutting edge of fluid dynamics, the Archimedes Screw demonstrates that a truly elegant solution is never truly obsolete. This mastery of mechanical advantage through simple rotation finds a parallel in another ancient system, one that used a different kind of circular motion to create immense power. A fortress wall could be shattered by a machine that harnessed gravity itself. The Counterweight Trebuchet was the crowning achievement of medieval siege engineering, a wonderfully elegant combination of immense force and precise calculation. Unlike earlier torsion-based catapults, its power came from a massive weight, often a box filled with tons of earth or stone, suspended at the short end of a giant pivoting beam. When released, this counterweight dropped downward, causing the much longer opposite arm to whip upward with incredible speed, launching its projectile from a sling in a high, arcing path. The true genius of the machine lay in its adjustability. Engineers could fine-tune the mass of the counterweight, the length of the throwing arm, and even the release point of the sling to achieve different ranges and impact forces with remarkable consistency. This was not a weapon of random destruction, it was a tool of applied physics, demanding a deep, intuitive grasp of leverage, pivot points, and mass distribution to transform stored energy into powerful motion. The legacy of this medieval giant is not confined to history books. The very same principles of storing and releasing energy through a rotating arm are alive in one of the most demanding environments on Earth, the deck of an aircraft carrier. Modern steam and electromagnetic catapults work on a similar, though far more complex, logic. They accumulate immense energy and then transfer it smoothly and rapidly to hurl a multi-ton jet from a stationary position into flight, a direct echo of the trebuchet's mighty heave. Robotics engineers also study these ancient systems to understand how to achieve precise, high-force movements using simple mechanical advantage, creating machines that can lift or throw with controlled power. The trebuchet stands as a monument to a time when wood and stone were guided by human intellect to reshape the landscape of conflict. After mastering the physics of launching objects through the air, another civilization perfected a technology for launching something far more enduring, the written word itself. Centuries before digital networks, a single machine in Mainz, Germany, began a revolution with the steady click and press of metal on paper. Johannes Gutenberg's printing press was a marvel of synthesis, combining the established technology of the wine press with the radical concept of reusable, movable type. This was not an invention born from nothing, but a brilliant recombination of existing ideas into a world-changing tool. By casting individual letters and characters from a durable metal alloy, Gutenberg created a system of type that could be arranged into pages, inked, and pressed onto sheets with unprecedented speed and consistency. Once a page was printed, the type could be disassembled and rearranged for the next project, making the entire process remarkably efficient. This mechanical reproduction of text transformed the availability of written knowledge. Books, once painstakingly copied by hand and accessible only to the wealthy and the clergy, could now be produced in the hundreds, then thousands. This flood of affordable texts fueled the fires of the scientific revolution, allowing researchers across Europe to share and build upon each other's discoveries with a common reference. It empowered the spread of new religious and political ideas, fundamentally reshaping the cultural landscape of the Western world. The true legacy of the press, however, is its core concept, the standardization and mass distribution of information. This principle is the direct ancestor of every digital platform we use today. The Internet, with its global, instantaneous sharing of data, is the spiritual successor to Gutenberg's machine, fulfilling the same fundamental human drive to connect, inform, and challenge through widely accessible knowledge. After a technology that so profoundly shaped the spread of words, it is fascinating to consider another ancient innovation that gave those words a beautiful and enduring physical form. A simple lodestone spoon floating peacefully on a bronze plate first revealed a force that would guide humanity across the globe. This was the earliest magnetic compass, born in China's Han Dynasty, a device that transformed the unknown seas from a realm of fear into a mapped network of possibility. Before its invention, navigators were tethered to the visible world, relying on the sun by day and the stars by night, utterly lost when clouds or storms obscured the heavens. The compass changed everything. It provided a constant, unwavering reference to magnetic north, a silent partner in the cockpit of every explorer's vessel. This reliable guidance unlocked the age of global exploration, empowering mariners to venture far from the sight of land with newfound confidence, connecting continents and cultures for the first time in history. The fundamental principle it harnessed is so profound that it remains utterly indispensable today. Every modern gyrocompass that stabilizes a massive container ship, every inertial navigation system that guides a jetliner across an ocean or steers a spacecraft through the void, traces its conceptual lineage back to that floating spoon. They are all sophisticated descendants of that initial spark of understanding, the realization that the Earth itself holds a directional force we can align with. This tool did not just point the way to new lands, it pointed toward a future of precise, automated travel. After such a tool provided a fixed direction for travel, another innovation would provide the means to calculate the distance traveled, merging the art of navigation with the certainty of mathematics. Long before the hum of a processor, the rhythmic click of beads on rods provided the world's first computational speed. The Abacus, a simple frame of wood and stone or clay beads, is a masterpiece of cognitive engineering. Its design is a physical expression of our base 10 number system, where the position of each bead carries a specific value. A user performs calculations not by memorizing abstract formulas, but by moving these beads through a set of logical, repeatable motions. This process trains the mind to visualize numbers spatially, to break down a complex equation into a series of small, manageable steps. It was, in essence, the first user interface for mathematics, a tactile bridge between human thought and numerical reality. While modern calculators give us an instant answer, the Abacus gives us a deep, intuitive understanding of the journey to that answer. This conceptual framework of decomposing a large problem into a sequence of simple, logical operations is the very heart of algorithmic thinking. Every line of computer code, from the simplest app to the most complex artificial intelligence, operates on this same fundamental principle. Programmers do not write a single command to solve a massive problem. They write thousands of tiny, precise instructions that the machine executes in a specific order. The Abacus taught us this pattern of thought centuries before the first computer was ever imagined, making it one of humanity's most profound and enduring cognitive tools. This ancient method of breaking processes into discrete steps finds a fascinating parallel in the next great innovation, a machine that broke the flow of time itself into a precise, automated rhythm. The steady, resonant tick of a mechanical clock marked a profound turning point in human history. Before their invention, time was a fluid concept, measured by the shifting sun or the slow drip of water. But in the monasteries and town squares of medieval Europe, a new technology began to carve the day into precise, measurable units. Driven by falling weights or coiled springs, these early clocks used a brilliant regulator called the escapement, a device that released the machine's stored energy in small, regulated bursts. This controlled heartbeat transformed a continuous force into a series of discrete, countable moments, allowing a clock's intricate gear trains to track the hours with remarkable accuracy. For the first time, society could synchronize itself not by the rhythms of nature, but by a shared mechanical pulse. Workdays, markets, and community life were reorganized around the clock's impartial authority, planting the seeds for our modern world of schedules and deadlines. The miniature engineering within these towers was a precursor to every geared system that followed. The same fundamental principles of gear ratios, escapements, and energy transfer are found in the automatic movement of a wristwatch, the precisely timed valves in a car engine, and the coordinated motions of industrial robot arms. They gave us the very concept of automated, regulated motion. This newfound ability to measure the Earth's rotation with mechanical precision paved the way for an even more ambitious undertaking, the measurement of the planet itself. A Roman surveyor could measure the length of an empire one pebble at a time. This was the genius of the ancient odometer, a device described by engineers like Vitruvius and Hero of Alexandria. It was a simple gear-driven mechanism attached to a cart's wheel. As the cart traveled, the wheel's rotation would turn a complex series of gears through a precise ratio. After exactly 1 Roman mile, the final gear in the sequence would complete a full revolution, tilting a lever that dropped a single pebble into a waiting container. At the end of a day's journey, the surveyor would simply count the pebbles to know the exact distance traveled. This was not a tool for personal navigation, but for imperial administration, allowing for the creation of accurate roadmaps and the meticulous planning that held a vast empire together. The principle is so fundamental that it remains unchanged in your own car today. A modern vehicle's odometer uses a sensor to count wheel rotations, translating that simple, repetitive motion into the digital numbers on your dashboard. This same logic of translating rotation into a precise digital count is the heart of industrial rotary encoders, the unseen components in countless machines that monitor the speed of a conveyor belt, the position of a robotic arm, or the feed of material in a factory. It is a bridge from the physical motion of a wheel to the abstract certainty of a number. This ancient drive to measure and quantify our world did not stop at the roads we travel, but extended upward to the very structures we build upon the land. These graceful stone arms embracing a cathedral are far more than decoration. They are a brilliant structural solution to an ancient challenge. The flying buttress allowed walls to become delicate skeletons of stone and glass, guiding the immense downward and outward energy of a heavy roof safely away from the building. Imagine the great weight of a vast stone vault pushing not just down, but also outwards against the walls, creating a need for strong support. The flying buttress acts as a brace, receiving this outward force and redirecting it in a graceful arc down into massive stone piers rooted deep in the earth. This externalization of support was a revolutionary idea, transforming a solid wall into a permeable shell filled with the breathtaking stained glass that defines Gothic beauty. This principle of managing structural loads through external bracing is now fundamental to modern engineering. You can see its logic in the soaring arches of massive steel bridges, where supports extend away from the main span to distribute weight and stress. More remarkably, this ancient idea is guiding the future of construction in extreme environments. Engineers designing concepts for large space habitats are exploring similar frameworks, using external trusses and tension systems to create strong, lightweight structures that can withstand the unique conditions of orbit, from microgravity to temperature extremes. The flying buttress reminds us that true strength often lies not in sheer mass, but in an intelligent design that guides force along the most efficient path. This mastery of redirecting immense pressures finds a parallel in the next innovation, a tool that applied precise, focused force to shape the very stone it was built from. The hardest substance in the natural world was once harnessed for the most delicate of tasks. As early as 600 years before the Common Era, master craftsmen in ancient India and China began embedding uncut diamonds into the tips of their drills. These precious stones, valued not for their sparkle but for their unparalleled hardness, became the key to boring perfectly smooth holes through the most resistant materials, from agate beads to ritual jades. This was a profound leap in material science, a clear understanding that to shape the unyielding, one must employ a force even greater. They had discovered the principle of the superior tool, using the inherent properties of one substance to masterfully work another. Today, that ancient insight echoes in the high-pitched whine of a modern dentist's drill. The bit that precisely shapes a tooth is almost certainly coated in synthetic diamond dust, allowing for clean, controlled work on one of the hardest surfaces in the human body. On an industrial scale, diamond-tipped saws slice through granite and composite materials, while diamond-edged blades are essential for cutting the ultra-pure silicon wafers that become computer chips. This enduring legacy demonstrates that the core challenge is often not the invention of a new process, but the discovery of the perfect material to execute it. After developing tools that allowed for such fine work on the physical world, another ancient innovation would turn its focus inward, creating a device that enhanced our perception of the world itself. A small piece of polished rock crystal from an Assyrian palace holds a secret that would take centuries to fully understand. Known as the Nimrud Lens, this 3,000-year-old artifact is ground into a slightly oval shape, a form that could bend light. While its true purpose remains a subject of debate, it might have been used as a simple magnifying glass to enlarge fine details for a craftsperson, or perhaps to concentrate the rays of the sun to kindle a flame. Its very existence is a powerful testament to early experimentation with optics, a first step in humanity's quest to see the world more clearly. This was not a sophisticated instrument, but a profound beginning. It represents the initial spark of an idea that light itself could be manipulated, that our natural vision could be enhanced and extended. From this single piece of crystal, a technological lineage stretches forward through time, leading directly to the eyeglasses that correct our sight, the telescopes that bring distant galaxies into view, and the microscopes that reveal the intricate universe within a single drop of water. The Nimrud Lens is a humble yet monumental reminder that our grandest visions often start with a simple, focused curiosity. This ancient desire to enhance our perception of life would soon be matched by an equally powerful drive to preserve life itself. Centuries before the age of industry, a simple device in ancient Alexandria captured the raw potential of steam. Heron's Aeolipile appeared as little more than a curiosity, a hollow metal sphere mounted between two pipes and connected to a boiling kettle below. As the water heated, steam rushed up through the pipes and into the sphere, escaping through two angled nozzles. The reactive force of these jetting vapors set the entire sphere spinning, a whirling metal prototype of power. It was a brilliant proof of concept, demonstrating that the energy within pressurized steam could be converted into continuous rotary motion. Yet for nearly 1700 years, this revolutionary principle remained a fascinating toy, its world-changing potential untapped. It would take the practical demands of a new era to unlock its true force, sparking the Industrial Revolution with the thunder of steam engines that ran entire factories and powered locomotives. Today, the legacy of that spinning sphere is more vital than ever. The same fundamental principle of using steam to drive rotation is the heart of our modern energy grid. Massive steam turbines spun by steam heated in nuclear reactors or by burning fossil fuels generate a vast portion of our global electricity. Even the roaring turbines of a jet engine operate on a similar reactive thrust principle, propelling aircraft across continents. Heron's invention was a seed of an idea, patiently waiting for the right conditions to grow into the technological forest that powers our world. This ancient exploration of internal energy for mechanical power finds a profound counterpart in a very different field, one that sought to balance the body's own vital forces. The cold, precise gleam of a Roman scalpel is almost identical to the one a surgeon might select today. Excavations across the former empire have revealed a remarkable medical toolkit, complete with finely crafted forceps for removing embedded objects, intricate bone drills for careful procedures, and speculums created for internal examinations that feel strikingly familiar. These were not simple implements, but instruments born from a practical, hands-on understanding of the human body, refined through experience in challenging environments. Their designs achieved an ergonomic excellence, balancing weight and grip to steady a surgeon's hand and maximize control, establishing functional standards that have quietly endured for 2,000 years. This lasting quality points to a profound truth in engineering, that when a form is perfectly matched to its function, it becomes timeless. The heritage of these tools is not only in their material, but in the very philosophy of medicine they embody, a commitment to precision that guides the development of advanced surgical systems and modern medical instruments today. This ancient drive to heal and understand the physical self finds a compelling parallel in the next great innovation, a technology that would shape not the body, but the architecture of human thought itself. An empty space on a counting board held a power that would one day build our digital world. The journey of zero from a simple placeholder to a full-fledged number is one of history's most profound intellectual revolutions. Early mathematicians in places like Babylonia and among the Maya used symbols to mark an empty column in their calculations, a concept of absence. But it was in India around the 5th century that this idea truly transformed. Thinkers like Brahmagupta began to treat zero not just as an empty slot, but as a tangible number in its own right with defined properties. He established rules for arithmetic with zero, explaining that a number added to zero remains itself, and the groundbreaking, though puzzling, fact that a number multiplied by zero becomes zero. This abstract leap gave zero its own identity and power. From India, this revolutionary concept traveled through the Islamic world, where scholars further refined it before finally reaching medieval Europe. There, it faced resistance from thinkers steeped in a philosophical tradition that saw nothing as a void that could not logically be a something. Yet its sheer utility for calculation and commerce eventually won the day. The true legacy of Zero, however, lies in the binary language that powers every computer on the planet. Binary code is a system of only 2 digits, 1 and 0. It is the ultimate expression of a simple, powerful duality, where 0 represents the off state, the absence of current, the closed gate. Without this concept of a meaningful nothing, this foundational layer of all logic and computation would be impossible. Every digital image, every line of code, every online transaction is built upon a universe of ones and zeros, a testament to the immense practical consequence of a once purely abstract thought. This intellectual framework for representing reality with simple symbols finds a remarkable parallel in the next innovation, a very different kind of code used to build a different kind of reality. The same meticulous logic that arranged zeros and ones was once applied to the Earth itself, with seed drills that planted a new future for humanity. Ancient Chinese agriculturalists engineered a remarkable solution to the age-old problem of sowing, moving beyond the less efficient practice of simply scattering seeds by hand. Their multi-tube seed drill was a horse-drawn implement that deposited individual seeds in perfectly spaced, neat rows and at a uniform depth. This was a revolution in precision. By controlling these 3 variables, spacing, depth, and alignment, the device created ideal conditions for every single plant to thrive. Seeds placed too deep would struggle to reach the light, while those too shallow could be lost to weather or wildlife. Random scattering created a chaotic competition for sunlight and soil nutrients, with weaker plants overshadowed by more vigorous growth. The seed drill solved all of this at once. The orderly rows allowed farmers to easily pass through their fields for tending, and the consistent depth ensured a reliable, strong start for each plant. The result was a dramatic surge in crop yield and a staggering improvement in efficiency, using far less seed to produce a far greater harvest. This 2,000-year-old concept is the direct mechanical ancestor of every modern planter you see rolling across vast farmlands today. The core principles of metered seed delivery, row planting, and depth control are the absolute foundation of modern precision agriculture. Today's sophisticated systems use global positioning and sensors to execute these same ancient principles with digital perfection, placing seeds in the soil with millimeter accuracy to maximize every inch of a field. This ancient innovation demonstrates that the path to sustainability and abundance often begins with a simple, yet profound, act of order. After such careful planning and sowing, the next great challenge awaited: the efficient gathering of the bounty. A simple rotation between 2 stones transformed the most basic of tasks. The Rotary Quern replaced the demanding labor of the saddle quern, where grain was prepared by moving a single stone back and forth. With its paired circular stones, one fixed and the other turned by a handle, this new mill could be operated with a smooth, continuous motion, a far more efficient transfer of human energy. But its true potential was unlocked when it was scaled up. By connecting the upper stone to a long lever, a donkey or ox could provide the power, turning a household chore into a shared community effort. Later, this same rotary principle was harnessed by water wheels and windmills, driving much larger millstones that could sustain entire towns. The core idea of 2 surfaces moving in a rotary, shearing motion to process material, is a mechanical concept so fundamental it has never been replaced. You can see its direct descendant in the massive industrial rollers that prepare ore for mineral processing, in the crushers that recycle concrete and asphalt, and even in the sophisticated ball mills used in laboratories. These modern devices use rotating drums filled with grinding media to reduce materials down to fine powders, essential for creating everything from advanced ceramics to vital pharmaceuticals. The Rotary Quern taught us how to harness circular motion for transformation, a principle that now turns the wheels of entire industries. Having journeyed through these 25 ancient technologies, from self-healing concrete to the first analog computer, a profound pattern emerges. This legacy matters not because these were isolated marvels, but because they represent a continuous thread of human ingenuity. Each invention was a response to a fundamental challenge, a solution born from deep observation and a willingness to experiment. They were not created in a vacuum, but built upon the knowledge of earlier communities, refined and adapted over centuries. This is the true lesson for our own era of rapid innovation. The past is not a static record to be memorized, but a dynamic library of proven principles. It reminds us that the most elegant solutions are often rooted in simplicity, in working with natural forces rather than against them, and in seeing the world not as a set of problems, but as a source of endless inspiration. The spark that lit these ancient fires is the very same one that drives us forward today. This enduring legacy of ancient ingenuity offers more than just historical fascination. It provides a vital blueprint for our future. These were not technologies created in isolated laboratories, but solutions forged through a patient and profound dialogue with the natural world. The Roman engineer understood that volcanic ash and seawater could create a material that maintains itself over time. The Persian architect saw how the wind and evaporation could cool a home. They worked with the forces of the planet, not against them, achieving a remarkable balance of efficiency and resilience. Today, as we face global challenges of resource scarcity and environmental change, these principles feel more urgent than ever. We are relearning that true sustainability is not merely a matter of adding solar panels to an inefficient system, but of rethinking our fundamental approach to design, just as these early innovators did. It is about creating buildings that manage energy like a wind catcher, infrastructures that endure like Roman roads, and agricultural systems that are as precise and thoughtful as the multi-tube seed drill. This is not a call to abandon modern technology, but to enrich it with timeless wisdom. The greatest innovation may lie in looking backward to move forward, in blending our most advanced discoveries with the deep, enduring intelligence of the past. The next time you marvel at a modern wonder, remember that you are also witnessing the latest chapter in a very old and brilliantly human story. From the self-healing concrete of Rome to the foundational idea of zero, these 25 ancient innovations reveal a powerful truth. The past is not a distant land, but a vibrant library of brilliant solutions waiting for our rediscovery. They remind us that human ingenuity, our capacity to observe, to experiment, and to persevere, has always been our most vital resource. As we navigate the complex challenges of our own century, from resource management to sustainable design, the most forward-thinking step we might take is a glance backward. We can learn from the masters who came before us, who worked in harmony with the world's natural forces to create technologies of profound elegance and endurance. If this journey through the echoes of ancient genius has sparked your curiosity, we would love to hear from you. Share your own favorite piece of forgotten technology in the comments below, and subscribe to continue exploring the fascinating crossroads where history and innovation meet.